everyone, this is Terminator, and as you can see, it's built to explore this arena and capture images of specific targets. Think of it as a high-tech scavenger hunt. But maneuvering isn't easy, especially for a robot the size of a small textbook. To avoid turning into a demolition derby, we needed brains, a clever algorithm, to handle it all. Our part was crafting the algorithm, a specialized A-star search that maps every possible path and assigns it a cost. Think of it as fuel efficiency. The longer the route, the higher the cost. And because this robot loves to turn wide, each turn adds up big time. We also penalize getting too close to obstacles. The goal is a smooth, calculated route for maximum image capture glory.
Simulations are one thing. Real-world robots are a whole new ballgame. Initially, even with perfect paths on screen, our Terminator took some creative liberties with his turns. To address this, we focused on collision avoidance. See these danger zones? They are our robot's worst nightmare. We implemented huge penalties to ensure it stays clear. But just being safe isn't enough. We want efficiency too. So, just like that delivery driver planning their day, we use something called the Traveling Salesperson Problem, or TSP. It determines the absolute best order to visit all those targets, creating the most efficient route with no crashes.
In this project, we're using the STM32 to control our robot car with precise movements and turns. By fine-tuning the motor control, we achieve accurate turns. Each movement is carefully calibrated using PWM signals to ensure smooth operation. With real-time sensor feedback, the car stays on track, making adjustments as needed for precision. So far, everything's running smoothly. But after weeks of testing, we've noticed something not so precise.
Well, the wheels were a little unbalanced, kind of like running with one shoe tighter than the other. This threw off our encoder readings and affected movement accuracy. We added a bit of weight to balance out things, like adding ballast to a boat. The results? Smoother, more consistent movements. Now, with balanced wheels and accurate movements, the robot navigates with a lot more confidence, no more wobbles.
Hey everyone! Ever wonder what happens when you give a Raspberry Pi an espresso shot? Well, meet our hyperactive robot brain. We have turbocharged this little pie with two secret ingredients: event-driven architecture and multi-process design. Our system is basically 5 different processors running at once, like my brain trying to juggle taxes, laundry, and remember why I took this module. We've got Android interface, STM32 movement, imaging, and command management all happening simultaneously. Thanks to this setup, our robot can handle multiple tasks at once, unlike me before coffee. And there you have it, a robot that's more organized than my entire life.
Need to teach a machine is ABC and 1, 2, 3? YOLO got your back. With Ultralytics YOLO model, object detection is as easy as looking one. But first, we label. RoboFlow makes it super simple. Just upload, tag, and export. Think of this as giving your model a cheat sheet. These custom Python codes work like magic, drawing stripes and embedding news backgrounds, making each image as unique as your morning coffee orders. In no time, our YOLO model is reading like a pro, whether it's spotting letters on stripes, or digits, or generic backgrounds. One look, that one is neat. Remember, you only look once, unless you are debugging. Then, good luck.
First, the app allows users to scan and connect to another Bluetooth device, ensuring a stable connection for communication between the phone and the robot. Bluetooth allows for wireless communication between devices, eliminating the need for physical connections. For obstacle management, users can manually input X and Y coordinates for precise obstacle placement. This data is sent in JSON format to a Raspberry Pi that controls the robot. Alternatively, they can interact directly with the arena using a tap and drag feature to plot obstacles, providing more flexibility in planning.
Additionally, the app allows users to save the current board configuration, reset it if needed, and reload previously saved layouts, which is useful for testing different scenarios without losing progress. Finally, once the start button is pressed, the app automatically plots the path provided by the algorithm team, integrating the solution and offering a visual representation of the robot planned movement. Our app receives checkpoints from the algorithm team. Since we only receive the key checkpoints, the app generates the full path internally. This allows us to display the robot's movement accurately on the arena, showing the complete route from start to goal.
This is our actual attempt on both tasks. As you can see, it did not go as smooth as we imagined. However, it was a great learning experience while meeting new people.